going to prove that there are an infinite number of prime numbers. And the best way to do such a proof is by contradiction. Assume that there are a finite number of primes. So we're assuming that. And if we get some contradiction, well, then we know our assumption is wrong. And say the finite number of primes are P1, P2, up to and including Pn. Okay, so now we consider the following number. P1 times P2 times P3 all the way up to, not plus, but times P sub n times P sub n plus 1. Okay, so we have this product plus 1. We have our sum of two numbers. Now, we know that P sub I going from 1 to n, we know that P sub I will go into P1, P2, up to P sub n, because it's one of the factors. Don't know what happened there, but this is for I equal 1, 2, up to n. So P sub I being one of those numbers, it's going to go into it. So P sub I divides P1 times P2 up to times Pn plus 1 if and only if P sub I divides 1, because P sub I divides this piece, so we must divide that piece as well. You know, a real classic, well, an example would be if you have this. 3 goes into 6. So we have 3 into, say, 13. Now, 3 goes into this. The only way 3 is going to go into 13 is if 3 also goes into 7. For example, if you had, I don't know, 9 and 18 and 27. Since 9 goes into the first one, the first term, the only way 9 will go into the sum is if 9 also goes into the second one. And 2 plus 3 is 5, which is exactly what 45 over 9 is. Okay. But P sub I does not divide 1. No prime number goes into 1. All prime numbers are bigger than 1. Okay. So the question is, so what can this number be? What can this number be? So what can this number be? Okay, and we have two choices. Either it's prime or it's not prime. 1. P1, P2, up to P sub n plus 1 is prime. Now, I'm getting tired of writing this number. Let's call it K. Now, I want to see if we said this. Now, each PI is greater than or equal to 2. So, that implies that what's bothering me? That implies that this product P1 times P2 all the way up to Pn plus 1 is bigger than P sub I being 1 to n. Okay, it's bigger than it. That means that this number cannot be P1, P2, P3, etc. Okay. So, now I'm not going to call it K. So, P1 times P2 up to Pn plus 1 is a new prime number. But that's the contradiction. We only have n prime numbers. The other case is P1 times P2 up to Pn plus 1 is not prime. But we know that every non-prime number, can be written as a product of primes, as a product of prime numbers. And hopefully you see the contradiction. But P1, P2 up to Pn plus 1 cannot be written as a product of primes from the list P1, P2 up to Pn, because for P2 to be a prime factor of this number, that means P2 must go into it. For 2 to be a factor of 3 times 4 times 5, 2 must go in. Oh, here. What's bothering me? For 2, 2 is probably not the best number to have used. Okay, for 3 to go into 3 times 5 times 7, it must have a factor of 3, because this prime number doesn't go into 5, it doesn't go into 7. The only prime number that 3 goes into is 3. Okay, it goes into 3. But no Pi divides P1, P2 up to Pn plus 1. So, but no Pi. So there must exist some other primes that multiply out to P1, P2 up to Pn plus 1. But this can't be. That's a contradiction. There are no other primes. It's just P1 through Pn. Hence, the number of primes is infinite. infinite. Now you may say, well, you know what? Why don't we just add this new number? Let's even assume for a moment it's prime. So at that point, we have P1, P2, up to Pn, and now a new prime. Well, this theorem that we just proved we could have used those numbers. So then there's another number, Pn, another prime number, Pn plus 2, and the list goes on and on. Okay, we can always come up with a new prime. Even if this number was not prime, so we have P1 up to Pn, it's a product of primes that don't include P1 up to Pn. So there's at least one other prime. Actually, if it's not prime, there must be at least two other primes. Okay, but maybe it is prime. So we have that one. And then this theorem says that there must be at least one more. Oh, this theorem says that you have this list. You must have at least one more. Well, that at least one more goes on forever. And we conclude that the number of primes is infinite. That completes this classic proof. Keep watching.